Hey, this is Joel Duff. Welcome back to the Dead Sea Chronicles Part 6. This time, all dried up when the Dead Sea died. So, in our previous exploration, we provided evidence for the existence of a very large lake, Lake Lasan, a prehistoric giant that filled the Dead Sea Rift to levels far, far above where we see today. And we've looked for 2 episodes at the evidence for that lake. How do we know how much higher it was, and when was it much higher in the past? We witnessed a landscape transformed by abundant water, reflecting a climate dramatically different than the arid region that we know today. But now let's turn our attention to the opposite extreme and ask, just how low can the Dead Sea go? Today, we see the Dead Sea just shrinking before our eyes, its shoreline receding year by year. But is this the lowest that it's ever been? What if I told you that this remarkable body of water, Earth's lowest elevation, deepest hypersaline lake, has been far lower than it is today, and that it's actually dried up, or at least almost completely dried up, multiple times in the past? Now, the Dead Sea, despite its present evaporation rate, seems so resistant to complete evaporation today. But it does contain evidence buried in the sediments below the surface today of times when it was reduced to little more than just a salt flat. In this installment of our series, we're going to look at the evidence for past desiccation events in the Dead Sea. We're going to explore how scientists have uncovered these dramatic episodes of the lake's history, and as previously, we'll ask how a dried up Dead Sea could be accommodated by young Earth creationism, although we're not going to spend a lot of time on that today. We're saving more of that analysis for a future episode. So let's dive in really deep, not just below the Dead Sea waters, but below the floor of the Dead Sea, down into the sediments that have been piling up eon after eon after eon, and see what those sediments can tell us about the history and the origins of the Dead Sea. Now, before we begin, let's do a little quick comparison of the Dead Sea with a place that my North American audience might be a little bit more familiar with, and that would be Death Valley. Right? Death Valley in California, another place that's below the sea level. It is a basin, so the water, say from the mountains in the background there, it drains down into this basin and has nowhere to leave, right? There's no river, no stream that leaves this area. The only way that this water leaves is it evaporates. I'm standing in front of a temporary water pool. This was in late March a couple years ago. So there had been some winter rains that had brought some water down into this basin that collected here into, as I just said, a pretty temporary pool, because it's going to be very hot soon, and this is going to evaporate much faster than the new water is going to be input, and we're going to have a Death Valley. All right, it's going to be very, very dry at this location. You can see the salt flats out here behind. The salts have been left behind after the evaporation of the H2O, the water. Here I am in another location. It's actually a little bit farther below sea level. This is really at the deepest area in Death Valley. And here what we see is a huge field here of what are kind of like boulders, but this is actually all rock salt. All right. So, and it was very difficult to actually climb out there. It was very, very sharp, like jagged rocks that were you feel like you're going to cut yourself if you weren't very, very careful. This is all the remains of evaporated salts from many, many years, actually many, many, many thousands of years of water collecting the basin, drying out, and leaving these salt precipitates. And the Death Valley and Dead Sea basins are somewhat similar in size in terms of catchment area. Catchment area would be like collectively all the area around it that when it rains, that water would flow toward the basin. But Death Valley is in a much drier area than even in Israel, right, in Jordan, and therefore there isn't even as much water that enters into this basin, and that's why most of the time it's dry, at the bottom. Now, there's another similarity between Death Valley and the Dead Sea, and it has to do with our previous episode, episode 5. This is a way for me to review just very briefly that 5th episode. We talked about how the Dead Sea Valley, right, and the Jordan Valley had a lot of water in the past, right? The lake levels were much higher, on the order of 500, 600, 700 feet higher, making a very large lake called Lake Lasan. And one of our evidences for that was that along the sides of the valley, right, there's basically these little bathtub rings of past beaches where the lake levels would have been. at higher elevations. And in this picture, you're looking at Death Valley National Park, and you're looking at what's called Shoreline Butte. So this is a large extension of this mountain sticking out here, a hill. And on the sides of this hill, you see these lines here. See these horizontal lines? Those horizontal lines you might think would be sedimentary layers, but they're not. This is in fact a volcanic, this is all volcanic rock, right? And that volcanic rock isn't laid down in horizontal layers. So what makes these horizontal lines is the fact that these are all different beaches. These all represent different places where there was a lake at one time in the bottom of Death Valley, or it was much higher, right? And it must have stayed at a certain water level for long enough that the edges of that lake lapping up against the rocks, against the basalt, actually etched their way into that basalt and created these shorelines. And that's what we're seeing here. We're seeing several dozen shorelines representing periods of time which the lake was at different stages in height. And of course, we don't have any recorded, we don't have any historical records of there being a large lake at the bottom of Death Valley. And there's no reason to think that it's been a large lake anytime in, say, the last 10,000 years. But potentially during the last ice age, and then before that, there was apparently a large lake in Death Valley. And that is why there's so many salts collected down there as well, because that would have been a large lake, more precipitation, bringing down more sediments, but also salt then dissolving from those rocks that are dissolving into the water. And then when the water has dried up, and it's kind of a similar story to Death Valley and the Dead Sea. Death Valley had water in it, then it dried up, then it had water in it again, then it dried up. So as the climate changes, goes back and forth between ice ages and interglacial periods, you ended up with times of heavy precipitation of salts when it dried up, leaving all this salt layer at the bottom that we see today. And if you drill down below the Dead Sea, below Death Valley, you'll find that there are many, 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 many feet of salts and other precipitates underneath it. But really nothing like the Dead Sea. I mean, the Dead Sea has, we've been talking about 15,000 feet, all right? 15,000 feet of sediments below the Dead Sea that have collected from the lakes that have been there in the past. All righty, so with the idea that the lake was much higher at one time, we're now saying, how do we know it was much lower than it is today? You see, the Dead Sea is a very deep basin. And even where the Dead Sea is today, it's still, there's 1,000 feet of water, right? Deep in the middle of the Dead Sea. So it still has a long way it could fall from where it is today. Now, to truly understand more of the Dead Sea's past, including our topic of the day, which is how low can it go, we got to look beneath the surface. And I'm not just talking about the surface waters of the Dead Sea. I'm talking about going all the way down 1,000 feet through the water, getting down to the bottom, the floor of the Dead Sea, and then drilling down below that to see all the sediments that have been piling up, right, ever since there was a lake present at the bottom of that basin. So enter the Dead Sea Drilling Project, right, the DSDDP. This was a scientific endeavor that has really revolutionized our understanding of this unique lake's history. Completed in 2011, the DSDDP recovered a continuous 450,000-year record of the Dead Sea sediments. So how did it do that? They basically take a ship out there in the middle of the Dead Sea, and they went to very much the center of the Dead Sea and the deepest point of the Dead Sea. Right? Dead Sea is a very large lake, and they wanted to get away from the shore where there's going to be a lot of sediments that are going to be dropping out because there's going to be sediments coming in from little streams around the side of the Dead Sea. And that makes the sediments pile up faster in that region. There also could be a lot more disturbance in them. And then what they want to do is look out at the center, more toward the center of the Dead Sea, because that's where the smaller particles and things that are precipitating in the water, minerals that are precipitating and then slowly falling down and collecting on the bottom, is going to form a fairly undisturbed record of sedimentation. And so they took a core. They just drilled down through the center with a hollow pipe, right? And then they pull those sections of pipe up and then pull out the cores, the sediments that are inside there. They're stacked on top of each other. So in 2011, they were able to core down about 450 meters. That's roughly 1,550 feet. And this has been a gold mine of information. And I'm going to show you, there's been multiple papers that have analyzed those cores for a variety of different forms of data and done a number of different types of analyses in order to look at environmental conditions in the past, to look at the amount of sulfur, to look at the amount of ash, to look at the number of, to do carbon-14 dating, there's all kinds of things. And I'm just going to show you just the briefest snapshot of some of those. Not going to feel very brief, but it's going to be like a brief introduction to what we can learn from these cores. But the main thing we want to learn is, how can we tell, looking at a core of sediment, how low the lake has been in the past, or maybe how high the lake has been in the past? Can we actually see what we saw in the last episode where I showed you the different benches, the terraces along the sides of the valley, representing different beaches? And from that, there was estimates made of like, okay, well, the water was up here and then it must have dried down. And so that meant there was a hotter, drier environment. Can we actually see the same thing in the sediments themselves? In other words, we're trying to find data that correlates, right? We're going to take different forms of data, but are they going to tell the same story? If they do, that strengthens our hypothesis about how the Dead Sea levels have risen and fallen over time. You see, the Dead Sea drilling cores reveal a really complex history. And what we're going to find is that the Dead Sea drilling cores does reveal a complex history of lake level fluctuations, including multiple periods where there was very low salinity. That would represent when there were high stands of Lake Lisson. High stands being when the water is very high. In other words, the water's diluted all the salts much more, so that would be low salinity. And then there's periods of extreme low stands, where the salinity is even higher than it is today, suggesting that the water is actually lower than it is today, that the lake was smaller than it is today. So all of that is a way of informing scientists as to what the environment was in this region around the Dead Sea, in this Dead Sea Basin area. Now, for our question here, right, about young Earth creationism, about the origins of the Dead Sea, about how long it's taken in order to form the Jordan Valley and the Dead Sea as we see it today, I think these findings have absolutely enormous implications and provide significant challenges to the young Earth creationist interpretation of Earth's past. After all, how could a flood cover this entire region, filling up the rift with water, but then somehow completely dry this entire area out prior to Abraham traveling to this region, just a few hundred years after the flood? As I've been saying in every episode, Scriptures actually gives us a reference point, right? It says that 4,000 years ago or so, Abraham and Lot are recorded as looking down into this valley and seeing what? The Salt Sea and the Jordan Valley, along with the Jordan River, right? They describe something that's very similar to what you and I would see if we were standing in their location today. All right, so that means that if I can show you evidence that the Dead Sea had actually dried up sometime in the past, and that past couldn't be after Abraham and Lot, but it must have been before, then how did a global flood cover the world and then somehow create this crevice in the earth, fill it with 6,000 feet of salt? We're not really going to talk about that. That's going to be below the 450 meters we're going to talk about today. We're just talking about the upper level of this, the sediments that are inside of the Dead Sea Rift. And so where does that fit? All right, this figure, again, we'll remind you, especially if you haven't seen other episodes of this series, we'll remind you of the enormity of the problem, right? We've been saying that the Miocene rocks right down here are represented at the surface on either side of the Dead Sea Rift. And then this whole area cracked open, right? That's the idea of a rift, right? And as it pulls apart, as the plates are moving and torquing a little bit and pulling apart, then this rock that's in between begins to fall as these faults begin to push away. That's why these arrows are pointing out. right? And as it pushed away, that forms the basin. And as there's a basin there, stuff starts to fill in the basin. And you have the Pliocene sediments, which are mostly salts. We spent a lot of time talking about like where did they come from? Pleistocene, and then the Holocene, which really only is the last 10,000 years, is the little bit of sediment that's on the top. The core that we're going to talk about today is actually in the, I'm not showing it very well, but it's actually in the Dead Sea. And it drills down 450 meters, which is not very far, relative to the overall amount of sediment that is inside of this basin, on top of what we could call the basic rocks that were there before the rift occurred. So we're just looking at the very top. You have to keep that in mind as I'm going to show you a bunch of pictures of these cores, and we're going to talk about features of those cores. We're really only talking about the very top layers. So whatever you imagine is the amount of time it takes to form everything I'm going to show you today, I'm still only showing you a small amount of the total amount of sediments that have to be explained by young Earth creationists. So here we go. Here's the ship. Here's the drilling apparatus. And there are multiple different locations that have been drilled. We're also going to talk about the En-Gedi core, which is right on the shore of the current Dead Sea shoreline. But these other ones are out in the middle of the lake, which is, you see here, the depth of the lake there, minus 728. That's not 728 meters below sea level. That's 728 meters below the surface of the Dead Sea. This is a very, very deep lake. By the way, you might be wondering, wow, how could that lake be so deep? I mean, it's like, here you got a basin, stuff runs into it. Shouldn't it be all filled up? By the way, so it didn't give me an idea of what is the sedimentation rate in the center of the lake. How much sediment actually falls to the bottom of that lake per year? It's on the order of like at most a centimeter, but usually just millimeters, right? Very, very, very small amounts of sediment reach the bottom of the center of the lake. Most of that's falling out around the edges. And so, yes, it would take a long time if you just say like, okay, if just things go as they are, how long is it going to take to fill up all this lake with sediment? Okay, so quick look at just, what some of these cores look like. So here we have several different segments that have been, pictures have been taken of. So remember, this is 450 meters, and you can see that we're only looking at 2 centimeters here. This section right here represents 2 centimeters. So 2, 4, 6, 8, about 8 centimeters, 7 centimeters for this whole thing right here. And so now you can see the very thin laminations, right? The very, very thin layers that are here. And these, in this case, these are aragonite and detritus couplets, right? And so aragonite is a precipitate that occurs at one part of the season, all right, the seasonality that goes on in this particular region. And detritus is sediments and debris that are brought in and sort of by flowing water, and then are taking a while to fall down to the bottom. All right, so you get this back and forth of lighter and darker, lighter and darker and lighter and darker. And you see like there's multiple layers even within 1 centimeter. That's why I was saying millimeters. Right. And this can be measured like current day measurements. You can take cores from the top, and there are ways to know, like we'll talk about in a future episode with seismites, in order to date certain layers definitively based on historical events. And then you can count up those layers above that and you see that they're basically annual rings. And so these couplets are annual layers. And so that's how we know that, there's only been, this 2 millimeters of material laid down at the bottom of the lake over time. Now, that's not true all the time in the history of the Dead Sea. Here we have a bunch of layers that are much thicker, right? Yeah. And then here we have gypsum deposits, which don't really have this layering to them. This would be, as gypsum is this soft, white, gray sedimentary rock, and that's made up of calcium, sulfur, oxygen, and water. So the lake has to be pretty dry, almost dried up in order for gypsum to start to precipitate out. into that mineral. And here we have halite. All right, so here would be a very thick segment. This is multiple centimeters thick of halite. That could be multiple years of salts that are precipitating out. So it's extraordinarily dry. There's not a lot of change in the environment, and maybe salt is precipitating out over a long period of time to form these particular layers. Here we have halite, which is salt, all right, and detritus couplets. So this would also be when the lake is probably shrunken way down. And because it's shrunken so much, you actually have salt crystals forming in the surface waters where it's even saltier because of evaporation. And those salt crystals are falling to the bottom, and then they're collecting. And then in this case, this is probably also seasonality, right? If there is a rainy season, then there's not going to be as much precipitation because the water is going to get just a little less salty when you add more fresh water to it. And so you're going to have, and because you've had sediments coming into the basin, which isn't just, sodium chloride, you also have small clay particles and stuff, right? Little bits of organic material. And they're being brought into the lake more so during the rainy season, and they're falling out. So you get a dark layer, then it gets really dry and hot. Then you have salt, and it gets, the rainy season again. And so these also are most likely annual rings as well. And you can see they're a centimeter or 2 centimeters in thickness as well per year. And you can see not all the core is halite and gypsum and aragonite. There's other things that precipitate out too. There's just clays and sands and other things. And that's going to represent other environmental conditions in the area. What just this one picture tells you is that the climate and the conditions under which the lake has experienced have changed a lot over time. And the neat thing about the aragonite and detritus couplets is we'll see in a few moments, we're going to see segments that have lots and lots and lots and lots of couplets. And then there'll be other stuff that's not annual rings at all. Lots of really dense precipitates. And then you might have a bunch of things like clay particles and so forth for a long time. Representing maybe a wetter time in which the water is filling up, bringing lots of sediment into the Dead Sea, and then it's falling out, and so it's accumulating a little bit faster, right? So there's lots of different morphologies, right? Appearances to the sediments telling you this isn't just like it all just happened at once, right? This represents significant changes in the environment around the Dead Sea. And this just gives you a broad overview of that 450 meter segment. And I've turned it on its side, mostly so you can see, here we have the Holocene. This is the top 10,000 years up here, which only covers 65 meters, right? 65 meters. Then below that, you have all this Pleistocene material. And then if you remember my figure before, there's the Pliocene, which is older rock below that. That's way down below 450. All right, we haven't even gotten down to the Pliocene. But I also want you to see it says Lausanne right here. Right, that's Lake Lausanne. This would essentially be up here is sort of the Dead Sea. Over the last 10,000 years, the Dead Sea has been the Dead Sea. It's gone up a little bit down, but it's basically looked the way that it does today. And then we talked in the last episode about Lake Lausanne, and that was really, we were talking about what we were saying, 14,000 years to about 70,000 years. All right, and that covers this portion of the column. And in that portion of the column, we have lots of gypsum layers. This represents salt being found in there. And then these, I think these gray bars represent the couplets that are found of the aragonite. I think I said aragonite before, aragonite. And then down here, way down here in the previous lake before Lausanne, remember I mentioned that Lausanne is only the most recent large lake, but there were other lakes that have been given other names. There's other slight criteria to sort of distinguish all these, but I'm not even going to do episodes on these other lakes. You can just think of these are older lakes, older lakes when the basin wasn't as deep. Because remember, the basin is falling all the time. So the farther you go back in time, the basin's not as deep. So it's sort of like you got a much more shallow lake in the past, even though it's higher up. A couple other papers. what are some other things that we're learning here? We're going to get to the whole, what is the evidence of it drying up? But let's talk a little bit more about these cores. So this paper from Quaternary Science Reviews, and you see that in 2020, looks very carefully at the lamina record. That would be the annual couplets, the portions of the column that you seem to be able to count years in. And so they are finding a record of 45,000 years of lamina records from the Dead Sea Basin. And that looks something like this. And so here in the Lake Lasan Formation, it's called. So the portion below the Holocene, farther down, deeper down into the core, we have the Lasan Formation. And here, this is showing a whole meter. Down here, extending out just this little segment right here. Here is 1 centimeter. Right. And so what they're doing is they have sliced the core. They've taken very detailed photography of this. And then you expand this even with a microscope. So you can see in this 1 centimeter, now you can see up close, and this down here is their calls, right? Each year isn't going to be the same, right? There's going to be more rain one year than another year, more input one year than another year. It might be hotter another year, more evaporation. And so maybe you get some more precipitates of various things. And so you're going to get different amounts per year, but nonetheless, you get this black, white, black, white, black, white, black, white, black, white, which they interpret as annual couplets. And so in this portion of the formation, we're seeing a lot of couplets over 1 centimeter. So this is 1 millimeter right here. So that's a thick couplet, 1 millimeter. And over here we have several couplets per millimeter. So just 1 millimeter represents potentially a couple years right there. In another portion of the formation, a little bit deeper down in the formation, we have some couplets that are much wider, right? So more deposition in total at that time. You might wonder, why would there be more deposition at some times than others? I just gave you one reason, bigger rainy season, but you're out here in the middle of the lake. Well, think about it this way. If the lake shrinks, okay, if it gets lower and lower and lower and lower, and it shrinks, then when you actually do still have rain and you still have inputs of sediment, when the sediment gets input into the lake, if the lake has shrunk, it's closer to the place where you're piling it up, right? And so you're going to end up with more sediments making it to that particular location. When the lake is very large, Lake Lasan, right? Lake Lasan was a huge lake. And we're drilling out there in the center of the deepest portion of the old lake, all right, of the center of the basin. Well, when sediments come down into Lake Lasan, right, they're going to be deposited all around the bathtub edge. Those are the sediments we saw in the last episode. We saw hundreds of feet of sediment all piled up in different parts of the Jordan Valley. And those parts were on the sides of the Jordan Valley, not right in the center of the Jordan Valley. Now, of course, there are sediments in the middle of the Jordan Valley from the Lake Lasan, but they are much thinner in terms of annual rings, whereas they're thicker toward the side. So if you're in one column in one place, though, you're accounting for then the changes over decades and years and thousands of years. You're looking at how much deposition there was. So this could be inferred in the Lake Lasan Formation. Because it was a large lake, yes, you expect to have very thin layers. Not much deposition out there in the middle of the lake. And over here, lots of deposition. All right, I've said that a few too many times. This figure from the same paper is reiterating the same idea that I just talked about. I'm pointing to two segments. These are two segments they looked at. This is where they're able to count those annual rings, right? Those Argonite detritus laminae. And you see when they occur. Just in the last 4,000 years, do you have a lot of laminae? And then back here, you have from 20,000 to 25,000 years. You also have a segment in there where they can count a lot of lines too. And that was during a time in which the lake was dropping. All right, when the lake is very low, you're going to get precipitation happening of minerals. And you're going to create a better chance of having these kind of laminae. And then also when the lake was very high, would be like at the high stand of Lake Lasan, or we mentioned that 25,000 years ago would have been when that particular lake was at its highest. And then it went on like a long period of just dropping, right, over a period of almost 10,000 years. And during that time, as it's dropping, right, it's getting drier and drier and drier. So it's in a dry environment. Things are evaporating, precipitation's occurring, and pretty stable in terms of its descent. And during that time, it produced a lot of these rings. And those are the ones we saw out there below Masada, right? On the sediments on the side of Masada, those are all laid down by Lake Lasan. And we see tens of thousands of couplets right there. Another paper looking at climate variability. This would just be in the Holocene, which would be just in the last 10,000 years. So we're just going to go to the very top of the core now. And I just wanted to show this because they show like their little representation of the different types of sediments that are in the column. And this is just for the last 10,000 years, which only covers, I've got to remember this now, the top 10 meters. The top 10 meters. 33, 32 feet or so. All right. So just the top 32 feet out of 15,000 feet of sediments that are in the basin. So the top 32 feet. And so here they're showing all these layers. This is all the aragonite detritus layers here. Right. And this is 1 meter. Actually, this whole thing is 1 meter right here. So this is 1/10 of a meter, right? So 10 centimeters here. So that's where you get your idea that these are, half a centimeter or less. And then here's a huge salt deposit right over here that only, what's this, 4.5 feet down. I'm sorry, 4.5 meters down. And here's the dating of those. So there's little pieces of organic material sometimes in the core. All right. So little plant parts or little pieces of insects or something that fell in and then fell down to the bottom. And then you date those using, say, carbon-14 dating. And here we're looking at 3,289 years before present. So you're just down 4.5 meters. You're already down 3,000 years. All right. If you go back to the time that Lot and Abraham are looking out there, you would be looking at, I got to go down here, somewhere in here. Right. And what that is this is all a lot of gypsum. During this time, you have clastic materials. You've got some salt. Right. You have salt granules, crystals that are formed right in here. That all suggests that, especially this layer down here at 4,200, right, which, Lot, Abraham, somewhere 4,200 to 4,000. This gypsum would also suggest the water was very, very low, like, as low as it is today or thereabouts. Right. So here you have carbon-14 dating saying that 4,000 years ago, you had the type of sediments being deposited at the bottom of the Dead Sea that would suggest that the Dead Sea was similar to where it is today. The Dead Sea has actually gone up a little bit since then. And in recent couple thousand years, it's actually been a little higher levels. And so that's why you have all these couplets of aragonite and detritus. It wasn't as low. And when it gets that low, that's where you start getting your gypsum and your salts and stuff like that. Right. So anyway, I'm just showing you that to show, like, even in just looking at the last 10,000 years, or in this case, 10 meters, right, 32 feet, only gets you back to like 6,400 years ago. 6,400 years ago. Of course, that already puts us back to creation in the young Earth creationist model. So they would have to deny these radiocarbon dates, which obviously they don't like radiocarbon dating for this reason. But we'll look later about how, the radiocarbon dating for the first 2,000 years doesn't seem to be very objectionable. And I'm going to show you a reason why we're going to line up the scriptural evidence of earthquakes, and we're going to see evidence of earthquakes in these cores. And some of those can be mapped to earthquakes that we know happened at certain years. And when you take that and you look at the radiocarbon dates, they line up. All right. That suggests that at least this first 4 meters, all right, just the first 4 meters gets you back 2,000 years. And so if there's another 4 years under that, you would think that's another, at least another 2,000 years. And so you get down here to just 10 meters and all of a sudden you're at 6,000 years. Like I said, this is only 32 feet out of 15,000 feet. And the main core taken by the deep sea drilling project is 450 meters. Not so 10 meters to 450 meters. 450 meters down, you're still getting couplets. You're still getting something that looks just like this. Right? So if these are real, and this represents, about that much time, a couple thousand years in the first 4 meters. And then you're seeing the same kinds of things 300, 400 meters below that. What does that suggest? It's just a whole lot of time has happened in order for all of this to accumulate. So they take that information, and what they're doing is they're saying, look, based on the types of sediments that we're seeing at different locations over the last 10,000 years, we suggest that in order for us to get this kind of sedimentation, these kind of sediments, in particular, these types of minerals that are precipitating, they precipitate at different concentrations. And so as the lake gets less saline, then different things precipitate out than when it gets more saline. And so that's what they're trying to record in that column. And then they're basically saying, okay, look, we were estimating based on the different things we're seeing in the sediments that this was the lake levels. And there's other people that have used other types of evidence to look at this and estimate the lake levels as well. And the rough profile really fits together pretty well, right? A little over 10,000 years ago, it was pretty darn low, like lower than today. Now, this isn't as low as we're going to go, because a little bit lower today is still not dried up. But it's still pretty amazing to think that today it's been on a steep decline, right? Just in the last 50 years, it's gone from 390 meters below sea level all the way down to 424 meters below sea level. But it looks like maybe 7,000 years ago was at least that low. And then 10,000 years ago or more, actually 10 to 12,000 years, it might have been below that, right? Deeper than that. But as recently as just 1,000 years ago, it was all the way up here at 370 and even potentially a little bit higher, right? So that's adding on another 100 feet higher than it is today. At that time, that would have been above some of the resorts that are there. All right. So it's like, they would have been underneath the water. But nothing like Lake Lassant, right? Which was at, up to, 150 meters below sea level instead of 370. The varves of the Dead Sea Sedimentary Record. All right. Varves is another name for, not all varves are annual rings, but most annual rings could be referred to as varves. And I showed this paper because I wanted to show this particular figure. They got a nice figure that tells us a little, I should have showed this earlier actually, that represents why do we get these couplets? Why do we get these couplets? So they're pointing out that there's sort of like 3 basic scenarios. So you could have a positive water balance, right? A positive water balance would be more water input during a year than it comes out. So the lake level is going up. And as it's going up, you still get aragonite, you get detritus, aragonite, detritus, aragonite, detritus. And then if you could have intermediate water balance, that's sort of like, it's pretty stable, right? When it's pretty stable, you end up with gypsum, aragonite, detritus. You get kind of a tri-layer. And then when there's a negative water balance and the water is receding, especially as it gets really low, eventually there's too much sodium chloride, and the sodium chloride then begins to precipitate and fall to the bottom and collect in these fine halite detritus that builds up over time and forms after it's compacted, eventually will form into halite, all right, which is like a whole become like a crystalline form, like a rock. All right, so those are your different conditions, and you get slightly different looking couplets under those different conditions. You saw there was a lot of other different conditions too. That would be, just a much more chaotic environment doesn't allow for these annual rings. That's what's going on at other times too. All right. So they looked in this particular paper at varves or annual rings. They count up something like, in the last 10,000 years, they can count up like 6,000 annual rings in that 10,000 year span. And most of them are these very thin millimeter width type things. Okay, we got to get to the main event. Just how low can the Dead Sea go? Or how low has the Dead Sea gone? So this paper from Earth and Planetary Science Letters from 2015, Dead Sea Drawdown and Monsoonal Impacts in the Levant during the last interglacial, by Torstein, and who's written many papers on the Dead Sea. Many of the really important papers that I've read have all been by this particular author and colleagues of his. And so here's two important figures from this paper. So on the left side, what we see is a cartoon of the entire 400, you're not quite able to see all of it, but the 450 meters that was cored from the middle of the Dead Sea. All right, below the Dead Sea. And so all these different colors represent graphically sort of like big, high level sort of changes that you see in the core sections. So you have these massive gray areas, and that is your thick halite deposits, like heavy duty, like mostly salt. That would indicate the water is a really low level at that point, very concentrated. Then you have other regions up here in which you have these aragonite detritus laminae. All right. And then there's other interspersed layers of salts. So that tells you like water was higher, water was lower, just like we've been doing. All right. So, but what we really want to notice is right here at, I think this is like 235 meters. 235 meters below, down this column, we find a layer of pebbles, right? Larger stones, right? Not really large, but, nonetheless, this isn't fine material. Now, remember, we're in the middle of a giant lake, right? We're in the middle of a large lake. So you got to ask yourself, how do you get pebbles? How do you get pebbles in the middle of a large lake? Now, what the figure on the right is the sedimentation rate. The sedimentation rate, the estimated sedimentation rate throughout the entire column. So no one's claiming that the sediments are piling up at exactly the same rate per year. Right? If it's saltier, there's more precipitation, there's evaporation going on, more salts are going to fall out one year than another year. If it's just all fresh water and there's not much input of new sediment, then maybe it's less than a millimeter per year. So you can have big variations in the amount of sediment laid down. But what they're looking for is a pattern over time. And so what they've done here is they've looked at, if you go down the core, you start at the top, and at the very, very, very top of the core, that's zero age, right? Because that's what's falling right now at the bottom and landing on the bottom of the Dead Sea. And then when you go down a couple meters, you're going down farther in time. I don't think anyone would deny that every layer you go down is an older layer, right? It's an older layer. Every layer you go down, the farther you go down the core, the older it's going to get. Now remember, young Earth creationists need to say that this whole core is 4,000 years old at most. All right, all of this has to be, under 6,000 for sure, but for sure this top section has to be well under 4,000 years. But in conventional dating, we've dated with uranium, thorium, carbon-14, so that's what these two symbols represent. And so they've taken little segments out of the core, found organic material in it, and then dated that with carbon-14 dating. And what these represent then is different dates at different portions of the core as you go down the core. And then they're just drawing a line through that and saying like, okay, if we have all these dates, we can see that there was a slope here that's very different than up here. So the sedimentation rate has been very fast over the last 10,000 years. For the last 10,000 years, we've had a lot of sedimentation. That makes sense. It makes sense because I've already shown you the graphics that showed you that for the last 10,000 years, the Holocene, the lake has been very low. Since the lake has been low, it's been small. Since it's been small, sediments coming into it are more likely to get closer to the middle of the lake and fall at the middle of the lake. And there's a lot of precipitation of things like salts, all right, and other minerals that are precipitating out of the water and falling to the bottom. And so therefore you expect it to pile up faster under those conditions. And then we had a protracted period where, boy, not as much fell to the bottom for a long period of time. And this is all the period of Lake Lasan, right? The lake was bigger. I know I'm being repetitive, but when the lake was bigger, you don't get as much sedimentation in the center of the lake. And so you went for all the way up here to over 125,000 years. And then you had this really dramatic, very dramatic amount of sedimentation occurring just after 125,000 years. What happens at 125,000 years? What's this break right here? Why is this clump of dates right here? That's right here, okay? That's right where these pebbles are. So the idea here is that right before that period, you had lots of sedimentation occurring. Now, this sedimentation is actually in the form of lots of halite production. Lots of salt is coming out of the water, being deposited on the bottom. How do I know that? Look over here, right below the pebbles. Wow. This is, that's 30 meters. That's 100 feet, 100 feet of salt, almost pure salt. That's only going to happen when the lake shrinks down to being very, very small and really, really dense. And now the salt is beginning to precipitate out very fast. All right, so you're going to have a much faster rate of sedimentation before that. So what it looks like happened is, leading up from 150,000 years to 125,000 years ago, the lake was shrinking, precipitating faster and faster and faster and faster. And boom, all of a sudden, there's not really much sedimentation for a little while here. It might have been hundreds of years, maybe 1,000 years, right? And then sedimentation begins again, but it's at a lower level than it was before. So it appears that the lake pretty much dried up, and here's the evidence the lake dried up. There's pebbles there. And why would there be pebbles there? Because if the lake was almost dried up, there certainly would still be a rain shower once in a while, right? There's still a Jordan River, albeit the Jordan River is probably a little tiny trickle. And maybe it was not even running all the time. Maybe it only had water during the rainy season. So it's kind of like the Death Valley. That's why I started with pictures of Death Valley, of that picture of me standing in front of a little temporary pond, right? And when there's a huge rainstorm and water comes rushing down the side of the mountains and eventually makes its way out into the middle of that flat basin and settles there, right? What does it do? It has an opportunity to bring, pebbles all the way out to the middle, right? Whereas when the lake was full, right, when Lake Lisson was there, or today the Dead Sea is there, water comes in, pours its sediment at the edge. The lake is rather placid, and the sediment starts to fall right there, and it doesn't get out to the center, right? There's no way that a layer of pebbles is going to make it all the way out there, thousands and tens of thousands of feet out into the middle of the lake to be deposited there. So that layer of pebbles says, there was a very shallow lake here. This thing is almost gone. You get pebbles all the way there. Okay, so as I said before, when was that? Maybe 120 to 125,000 years ago. Didn't use carbon-14 dating. It turns out after you get past 50,000 years, the carbon-14 dating is useless on organic material there. So you have to use uranium, thorium dating, and other metrics, including those stromatolites, because you can correlate the evidence from Lake Lisson. Well, this is actually before Lake Lisson, right? Lake Lisson only goes back 70,000 years. So we're actually before Lake Lisson and a time which was well before the last ice age. So we're in an interglacial period when it was much, much warmer. And that's the idea, is that during that really warm time, all of it's pretty much dried up. So now you're looking at it. Before I just showed you the last 10,000 years right over here. So we were just looking at the changes in lake levels right in here. But if you go back, this is Lake Lisson, or Lisson, right, going back to 70,000 years. And then as you go back, there's other lakes, but some of those dried up. And here's what we're indicating right here at 120,000 years ago. There's a deep dive, humongous amounts of salt precipitation, and eventually ending up with the Dead Sea being basically completely dead. and then a pretty quick rebound, right? The environment changes, more water input comes in, the lake begins to fill, and as it fills, it's filled with fresh water at that point. You don't get you don't get the couplets, you don't get a lot of precipitation of salts, so you don't have a lot of deposition in the center of the lake at that time, until things sort of even out again. All right, so there's been studies that have looked at like the thermodynamics of this. This whole paper is a bunch of math showing like what it would take to dry up the Dead Sea, and it would take a lot. It would take a very hot environment, a lot of evaporation. Really, the lower the lake goes, the heavier the air over it is. There's more humidity maybe stuck down in the basin, which reduces the amount of evaporation. So you would have to cut off almost all water supply to the Dead Sea Basin for extended periods of time. You could have a little trickle each year in order to get it to go as low as it was at that particular point, because that could be hundreds of feet below where it is today. And under today's conditions, we think that the Dead Sea will keep going down, but it will reach a level where it really can't go much lower with the amount of water that's still coming in from the Jordan River. All right, so now turning my attention quickly to a little bit of a response from Young Earth creationists, although I'm saving the bigger portion of the response to these cores for later. When we talk about seismites and we talk about a few other things related to that. But I just want to briefly mention this particular article from Institute for Creation Research. So here's Brian Thomas, and he's talking about the Dead Sea sediment core confirms Genesis. And what he's talking about here is he saw this paper, the one I just showed you. All right, this one right here from 2015. And there was a popular press article that went along with this. The Dead Sea dried up, long ago. When they found evidence in the deep sea cores, the Dead Sea cores, that it was completely dried up. And so, of course, Brian Thomas comes out and says, Dead Sea sediment core confirms Genesis. You might wonder, how does that confirm Genesis? Israel's Dead Sea, also called the Salt Sea, lies over 1,000 feet below sea level. Some scientists thought that the sea was too salty to have ever dried up, since such extreme saltiness would presumably prevent all the water from evaporating. Now, a deep drill sediment core appears to show that they were wrong. He acknowledges that at 235 meters below the floor of Dead Sea, there is evidence that it dried up. And he thinks this happened during the time of Sodom and Gomorrah, because he thinks that the scriptures record that during Sodom and Gomorrah, there was immense amounts of salt laden in the land. Now, of course, if there were civilizations at the Dead Sea or a little bit below the Dead Sea today, there are theories about the Dead Sea being higher than it was in the past and actually covering over Sodom and Gomorrah that are recorded in scriptures. But either way, there's salt around the Dead Sea today. But anyway, he looks at it and he goes what he did was he saw this article and he thought, well, people are going to hear about this. How are we going to explain how the Dead Sea could be all dried up? Well, maybe sometime in the past it was dried up, and maybe in Sodom and Gomorrah was a especially salty time. And so I'm going to talk about this paper a little more later, but I just want you to think quickly about what I've said and whether this would fit at all. I mean, did Brian Thomas think about what he was saying, 235 meters below the Dead Sea level? I just showed you in the top 4 meters. The top 4 meters covers the last 2,000 years. All right, and I think I can completely convince all of you that that's the case with some pretty strong evidence. Right, and then the radiocarbon dating, all kinds of other things suggest that in those top, 20 meters, right, you've got, 20,000 years. Right, this is 235 meters below the surface, filled with thousands and thousands and thousands of these couplets. And there's other places in there where there is immense amounts of salt, like close to a meter thick of salt. And I showed you that the Dead Sea was probably lower just maybe 8,000 years ago. Right? So really it might be that 8,000-year-old age that might be more. That's a whole lot closer to the Sodom and Gomorrah time of the Bible in terms of the timeline, right? The chronology. So maybe that is the time which the Dead Sea was even saltier than it is today. But for him to just come out and say, well, if 235 meters below the Dead Sea, maybe that's when it was all. So he has to propose then that 235 meters of material, all that stuff, all those sediments have piled up since Sodom and Gomorrah. So over the last 4,000 years. And yet scriptures record for us that the Jordan Valley has been kind of similar to what it is today over the last 4,000 years. Right? How much sediment could the Jordan River really bring into the Dead Sea Basin? 235 meters to coat the entire bottom of the Dead Sea? When we know that the current rate of deposition is on millimeter scale, and I'm talking about 50 years ago. Today it's even less because even less Jordan River water is getting in there. This is where all of this gets really preposterous, right? The explanations that young earth creationists have, and I'm going to show you more. I'm going to show you a young earth creationist that completely and utterly contradicts Brian Thomas, because I don't think Brian Thomas, thought at all, didn't look at the column, didn't look at anything about it, didn't look at the salt layers. He simply took an article he heard about and tried to come up with an explanation for why that is. So with that, it's been kind of a long episode, much longer than I thought it would be. We're going to turn our attention to Sodom and Gomorrah. And that's going to give me an opportunity to talk about the seismic history of the Dead Sea. We're going to see in the sediments of the Dead Sea the recording of large earthquakes. And that's also going to help us date the sediment core itself. It's also going to form a really powerful evidence of some of the large earthquakes that are recorded in scriptures. But we're going to see them all, and just to give away part of the story, guess where all those earthquakes are going to occur, right? All the evidence is going to be found in the top 5-6 meters of sediments out of the 15,000. All right, so put your thinking caps on, young earth creationist. I really am interested to find out where you think the prior 15,000 feet of sediments came from. And where they're going to fit into the chronology of the Dead Sea. All right, the Dead Sea Chronicles, Part 7, Sodom and Gomorrah and the seismic history of the Dead Sea. We'll see you when we see you. Bye-bye. Thank you for watching this installment of the Dead Sea Chronology series. As we've explored today, the Dead Sea region provides fascinating insights into Earth's history and raises important questions about how we interpret both scientific evidence and scripture. If you'd like to dive deeper into this topic, I invite you to visit my blog, Naturalis Historia, at thenaturalhistorian.com, where you'll find detailed articles exploring each aspect we've covered today, including full references and additional resources. Here's the schedule for upcoming episodes in this series. Each new video builds on what we've learned today, helping us better understand how geology and questions of the Earth's and our origins intersect in this remarkable region. You can learn more about my work and background at joelduff.org. If you found this content helpful, please consider subscribing and sharing with others who might be interested in exploring these important questions about science and faith. Thank you again for watching. Blessings to you and all who are around you.